tomorrow we have office hour. If you have any questions, I don't know. What else? Yeah, that's it. Okay. So on Tuesday, we finished off with defining the norm. Vector space. Today we'll mostly focus on the vector space continuous functions on some interval and equipped with the supernorm. What's the supernorm? It's the maximum. So this is AV, and it's this guy, this value. So we'll do some examples and prove that continuous functions are complete with the supernorm. Okay, so first some definitions. The chapter 2 on topology actually carries through to norm spaces simply by changing the definition of the ball, the metric ball. So we define a metric ball on V with the norm is this a metric ball on V at a point V in V is the set X in V such that the distance in the supernorm, in the norm, is less than R. So in Euclidean, we just have the ball, right? The usual ball. But now we're in arbitrary norms. So let me do a concrete example. For take continuous 0, 1 with the supernorm. Then what is the ball, the metric ball at the function 0, just to simplicity. So what is it? So let's write down the definition. We have radius, and we put the 0 function. So this says take all the functions in continuous such that the distance of f from the 0 function in the sup norm is less than r. Okay. Okay, so what is this? This is just all functions, all continuous functions with sup bounded by 1, bounded by r. So pictorially, let me draw it. This is 0, 1. This is an arbitrary continuous function. And this is the bound r. So, how do you say this? And then minus r. So the ball is this guy. It's all, functions that are within this image. Is that okay? So things are a little bit different with function spaces, but hopefully we will get a handle on the geometry, the topology on function spaces. Let me do another example. Take, let's see, just take a constant function like 1. And then BR of 1 is same, right? All the functions that are distance r. 1, i.e. sup in x0, 1, f of x minus 1, is less than r. So pictorially, what you have to do is you first draw the function 1, and then you go up 1 plus r, and then you go down 1 minus r, and this is 0 to 1, and you're asking that all the functions are within this image. Now let me do a little bit more complicated example. Take g of x to be the constant function. Then similarly, f in BR of x are all the functions f minus x, distance r, which is sup x in 0, 1, f of x minus x is less than r. Okay, so now let's draw the picture. So this is x, It's a little bit big. So this is X. And then, right, so now you draw the ball in this way. So let me erase this to not confuse you. Right, so you say it. This is 0, and then, okay, you can go down to minus R. You don't go up to R. And, right. So let me do this carefully. So this is 1 minus R. This is minus R. And go up to here. All right. So, okay. So now we're asking to be distance R from X. So all the functions will be inside this tilted ball. Is that okay? Okay. So you can imagine more generally, if you want to have some intuition, for the function, the ball PR of G, pictorially it would be, so it's hard to draw exactly, but so let's say this is G. It's very complicated. G. Then you you sort of look at the shifted G. I know my drawing is a bit bad, but I hope you understand. And then we're requesting all the F's to be inside here. We use a different color. This is F. F in, so let me make it blue. F in BR of G. Does the entire function have to be contained in that region or just the supremum? Well, you can answer this. So if the supremum is in it, what about the function? What do we know about the supremum? Yeah, you can answer this. Yes, it will be, but why? I mean, that's what we've been drawing all this time. All right, then definition for open. A set S inside the vector space is open if chapter 2 follows, so same, around every element in S, there exists a metric ball BR of G such that the ball is fully contained in the set. Right? So that was the same as in chapter 2, where a set S is open. If given any point, you can draw a ball that is fully contained in the set. Okay. Good. So things are very similar. So let's do some examples. Let S be all the continuous functions with the additional property that they're strictly positive. Claim S is open in V in continuous functions with the sup norm. So you always have to specify the sup norm. I mean, you have to specify the norm because it specifies the metric ball, which specifies the topology. I mean, okay, let me continue this remark because it's important. So you might have sets that are open with one norm but not another. And I think we will do some today. With one norm. But not another. Okay. All right. So let's show that this function is this set is open. Yeah, I can continue here. All right. First, right. First, so yeah, this is one to show. Claim for each f, there exists a constant epsilon f such that f of x is bigger than epsilon f for all x in 0, 1. Then we'll use this epsilon f as the radius for the ball. Okay, so let's see. By way of contradiction, suppose that, you know, for each epsilon n equal to 1 over n, there exists xn in 0, 1, such that in fact 1 over n is bounds f of x or n, and yet you're still strictly positive. So the strictly positive will give a contradiction. Let's see. Okay, so since 0, 1 is compact, there exists a subsequence converging subsequence. X and K going to L within 0, 1. So that was the definition of compactness on the reals, which is the same here. So yeah, so we have this definition that a set is compact if every sequence has a converging subsequence. Okay, but F is continuous, so by sequential continuity, f of x and k goes to f of L in f of 0, 1. Okay, but somehow this guy tells us something. It tells us that f of L is, in absolute value, is less than f of L minus f of x and k plus f of x and k. Now this guy we know. So this one we can control by epsilon over 2 if you like. So, and then this guy, you know, is less than 1 over nk. So now just take the limits if you like. You can just take limits here, or you can just write it as epsilon and then take epsilon to 0. Here take 1 over nk less than epsilon over 2. So we get f of L is 0. But that contradicts f of x is strictly positive for all x in 0, 1. Okay. All right. If you have questions, just tell me. I can go over things again. You know, we can do this slowly, more slowly. So just tell me. All right. Right. So we proved the claim. So for every f in S, f of x is bigger than epsilon f for some f, for some constant. Okay. Now we want to show S is open. That means around every f in S, there exists a ball. So there exists a radius and a ball that is fully contained in the set for some RF positive. Okay. So let's see. What do we have? Take G in this ball. Let's try to figure out, so we want to find RF. So take G in this ball. What does that mean? It means that G minus F in the supernorm is less than RF. So now we're reverse engineering. What does that mean? It means, how do you say it? Yeah, it means that, so sup of x01, g of x, f of x is less than r of f. In other words, you have minus rf, g of x, f of x less than rf for all x in 0, 1. Is that okay? Any questions? Where did the 1 over nk come from? Okay. Good. So it came from over here. Too slow. So we wanted to prove this, and the negation of this is that as you pick epsilon small, you can always find a point below that line so that this is satisfied. So let me draw a picture. Let me move this. So let me draw a picture of what we're saying. You give me any 1 over n. We can find a point where the f dipped below. Is that okay, Ahmad? Okay, so that's the definition of the sequence. And then, that's the xn we're working with. And so that's the bound we got from there. I think there's a lag. All right, so, okay, we have this. And so g of x is bigger than f of x minus rf. Now, we want this to be positive. How can we do this? Well, we know, so we know that f of x is bigger than epsilon f. And so set rf to be epsilon f over 2. So we get g of x is bigger than f of x, rf, which is equal to f of x minus epsilon f over 2, which is bigger than epsilon f over 2. And so we got the strictly positive, which implies that g is inside S, which were all continuous functions, such that f of x is strictly positive. Okay, any questions, comments? So that's how the typical question goes. You have to play around with f to figure out the radius. Okay. All right. Let's see. We have some more time. So I'll do an example of closed. So let me define what closed means. So it's the same as before. A set S inside V is closed with respect to the norm if any Gn in S satisfies Gn minus G goes to 0, then we require that the limit point G is also in S. Okay. Right. So let's do an example. Again, supernorms, because that's what we will be doing for most of the course. Take S to be the continuous functions. But all of them are fixed to be 1. So pictorially, it's very nice. What is it saying? Go to 0, 1, and they all branch out like this. So this is 1. Like that. They're all fixed to be, this is G, H. They are all equal to 1. Okay. I want to show S is closed. A general remark is that when you see equality, the set is often closed. And then when you see strict inequality, it's open. So that's as a heuristic if you want to figure out whether it's open or closed. It could be neither, of course. Because I remember this was coming up sometimes from previous courses. Okay, I want to show is closed. That means take a convergent sequence. How do you say it? Gn in S, such that Gn goes to G in the continuous. I want to show G is also in S. Okay, so this question is actually very manageable. How do we do this? So right. So in other words, we want to show that G of 0 is 1. So this has to equal 0. So do a triangle. And you have G0 minus GN0 plus GN0 minus 1. Okay, so far? And I think it's clear, right? This guy is 0, because by definition, because Gn in S means Gn of 0 is 1. And then just take limits. So this is less than epsilon. And so we get G0 is 1. Okay. I think enough examples. So here there was a subtlety that maybe you caught, maybe you didn't. A priori, this statement is not obvious, that in fact G is continuous. So this is a very subtle statement, and we will prove it now. Proposition, uniform limit of continuous functions is also continuous. That means suppose Gn in C01, the interval doesn't matter, but it's more convenient, such that Gn minus G in the supernorm goes to 0. Then G is also continuous. Okay. All right. So let's try to prove that. Next week we'll prove completeness, and this lemma is this proposition is a fundamental piece. Okay. Okay. What do we want to do? For all epsilon, so fix epsilon. I want to find delta or R, whatever you're comfortable. So fix epsilon, sorry, fix epsilon and x naught in 0, 1. I want to find R, depending on epsilon and x naught, such that if you have x minus x naught less than R, then g of x minus g of x naught is less than epsilon. Okay, questions? So this will be an epsilon over 3 argument. Okay, let's see what's happening. So let's do a little bit of reverse engineering. We have g of x naught, and then let's subtract the limiting sequence. Like, and plus g of x naught. All right, so we have to control each of these pieces. Let's start from the, these two are easy. So let's start from them. By, how do you say, by Gn going to G in the sup norm, we have the following. How do you say it? For epsilon over 3, there exists n epsilon over 3 such that this is 0. So this is less than epsilon. So let me write it as sup. Epsilon over 3. So right away, going back to that question, we have epsilon over 3, the remaining piece, and this guy plus epsilon over 3. Is that okay? Right, so it remains to control this. All right, right. Good. So first, for simplicity, take n to be n epsilon over 3. Just to make things simple. Okay, and then what do we want to say? For epsilon over 3, since G n is continuous, there exists R for this function. So call it n epsilon over 3, such that, you know, x minus x naught less than this R gives G of n epsilon over 3 minus G of n epsilon over 3, x naught is less than epsilon over 3. Let me put this as n because it's a bit confusing. Okay. So we're almost there. So our so set, we found the R. So set R epsilon x naught to be this R of n epsilon over 3. Then indeed, x minus x naught less than this R gives us epsilon over 3 plus, you write n, so this is from here. And this is epsilon, they sum to epsilon. Any comments, questions? Is that okay? Anything? Sure. I hope someone, okay. How did you get the gnx0 minus gx0 is less than epsilon over 3? Thank you. So Gn is continuous, right? That means that if we give you epsilon tilde, you can find there exists R epsilon tilde. So that you have this, if I write as epsilon tilde, so that you have this statement, because Gn was in C01. Is that okay, says Jan? Finishing up, let's, I think I have worked a few minutes, so I can do a little bit more. Yeah. So now let's prove C01. Okay, first let me define something, sorry. Definition, a set S is complete with respect to the norm if every Cauchy sequence in S converges in S with respect to the norm, right? So everything's the same. Just wherever you see absolute value, put the norm. So chapter 2 is identical up to this change. Okay, so then we have a beautiful theorem. The space of continuous functions, the norm space, the space C01 equipped with the sup norm is complete. So let's try to prove this. Do I have time? No, we don't have time. Okay, so I'll continue on Thursday. So yeah, I'll stick around for questions, and otherwise I'll see you tomorrow or Tuesday. So I'll stick around here. I would like, no, tomorrow is homeworks, not now. Anything? Yes, thank you. Is it important that we're working with these continuous functions on compact intervals? Right, thank you. I don't know if, I'll probably put it in the notes, but there are things that you lose when you don't have compact. So, what do I want to say? Yeah, so when we remove compact, we can lose limit points. So what's a good example? I have to think a little bit. I had some nice examples, but you know, you want something that there was something like, let's see, so maybe like x over n, and then something weird happens where this guy converges to the step function 1, 0. So yeah, let me try to find some nice examples. Yeah, we can lose boundedness, exactly. Exactly, yes, absolutely. Of course, that's even, thank you. That's actually more important. So for example, x is in C0, 1 with a sup norm, but it's not in you know, CR sup norm. So we lost the identity function. Thank you, Ahmad. That was very nice. Can I ask about previous lecture notes? Yeah. Is it okay if I ask you to briefly? No, I said, Austin, tomorrow for homeworks. If we want to prove a function is not uniformly continuous, can we choose xn, yn? Let's see. No, that's a good question, Sangu. So you must always ensure that, okay, so f is UC, if and only if xn, yn going to 0 implies f of xn, f of yn goes to 0. So you definitely need this. Now, of course, you can add other properties, but this should be one of them. You can add, I don't know, for example, maybe you want xn, yn to be 1 over n, or is that what you said? So yeah, they can go faster, but they have to go to 0. Sangu, is that what you meant? Sangu? Can I choose xn such that xn is bigger than 1,000? Okay, that's a little bit tricky. Oh, I see. Yeah. So yes, of course. Let me say this more clearly. But yeah, to break UC, to break UC, you just need to find an example. Any example will do, even the one. You just need to find an example, like we did in the lecture notes on Thursday, on class with 1 over x of xn, yn, so that even though these guys go to 0, you know, you can even have what you said, like that's fine. But the main thing is this, yet this guy is like lower bounded. Yeah, I mean, you can add it, right? But that's like an extra thing for your purposes. the only thing you need to ensure, this only thing we need to ensure, only requirement to ensure, you know, how do you say it? Like if you want to break uniform continuity, you just need to find something that has this, yet breaks this. And yeah, maybe you needed that to do this. That's fine. Okay. What else? In chapter 3, we need to use MVT, but isn't MVT depends on continuity? To prove continuity. Is it from my 1.11 in chapter 3 handouts? Chapter, you mean tutorial handouts or class notes? Yeah, MVT requires continuity, so that's, let me try to find it. Yeah, 1 second. I'm trying to find what you wanted. Actually, can you tell me the page so I can find it? Kin Yang? Page 3. I don't see any class handouts. I don't know exactly. Do you mean the hand example 111? Oh, I see. Yeah. Then we get that this is continuous. Oh, yes. How do you say this? Oh, I see what you're saying. No. I wrote I should have said is, I will correct it, uniformly. Yeah, I will make the correction. Yeah, clearly, yeah. MVT doesn't necessarily give you, how do you say it? Yeah, like you need continuity to have MVT, but you don't need uniform continuity to have MVT. So I will write uniformly continuous. That's what it gave us. Give us a lot more than continuity. But yeah, we assume it's continuous. King Yang? Okay, yeah. Oh, I see. You're right. So I have to, yes, thank you. I have to move this example later to below. Thank you. Yes, that's a very good point. I will. Okay. I don't think we have an official. No, it's the same from calculus. Whatever you had from, but I will write it. But it's the same one you had in calculus. You know, with the slope. No different. So, but I'll write it as well. Okay.